Hello students, welcome to the amazing platform of Physics Wala. Welcome to the PW English channel, my dear students. We are on the lecture 2 of solid state. I hope all of you have understood everything in the first lecture. First lecture was super easy and it was all theoretical. I tried making you explain each and every point so that you'll remember it for life, right? Yes. So now, my dear students, today we are on the lecture 2. What are we going to discuss? We have discussed the different types of solids, amorphous solid and crystalline solids, and also we also know from here that your amorphous solids are just 1% of the all solids present. 99% of your solids are crystalline solids, and that is the most important reason for us to discuss crystalline solids in detail. After that, we started discussing about the crystalline solids, and we classified the crystalline solids in 4 major solids. First was ionic, then it was molecular solids, and then metallic solids, and then covalent solids. We will be discussing each and every type of solid today. We have discussed ionic solid. Today we'll continue the further process. Okay, I hope all of you are excited. Let's start the amazing session. So the second type of solid that we will be discussing is the metallic solid. So let's try to understand what exactly is a metallic solid. So my dear students, we all know that what are metals? Elements, those have the tendency to lose electrons. Metals generally have the tendency to lose electrons, or we could say that they have a valence electrons that they are ready to lose, right? Yes. So my dear students, we'll understand about metallic solids. Let's take example of metallic solid. Zinc is an example of metallic solid, my dear students. Similarly, let's take sodium. Sodium is also an example of metallic solid. Now I'll explain you what these does. Okay, the second thing is constituent particles. What are the particles, my dear students? They are metals, right? They are elements. Yes, I hope you're clear with this. The constituent, can I write it here, metals? Yeah, metals are your constituent particles. And what is the force of interaction? The force of interaction is, my dear students, metallic bonding. Can I say the force of interaction is metallic bonding? Yes. So let's say that it is metallic bonding. Now I'll make you explain everything. Now let's try to understand what a metallic solid is. Okay. Yeah. So now, my dear students, to understand metallic solid, let's take an example of zinc. Okay, zinc is a metal. Zinc is a metal. Okay, so ma'am, zinc is a metal, and zinc has a very high tendency. Since it is a metal, it has a tendency to lose electrons. So what does zinc do? Zinc loses 2 electrons, right? Yes, let's say electron is here and electron is here. There you will have another zinc which will again lose 2 electrons. You will have electron here, somewhere electron here. Let's say you have zinc 2 plus here, and it will lose electron somewhere here, somewhere here. So basically what happens is your metals lose electrons, and they are present in the sea of electrons. Those electrons don't have a definite place to be present. They are present randomly in a particular surface. So you have Zn2 plus and you have the sea of electrons around it. Okay, you have various Zn2 pluses and you have electrons present around it. This is how a metallic solid exists. Okay, and there is an interaction between these electrons, and this is what is known as the metallic bonding. Okay, so now let's try to understand the metallic bonding a little more. Okay, so if you see these positively charged ions present in the sea of electron, they are also known by a name which is known as kernel. So you need to write this down. Positively charged ions present in sea of electron are known as kernels. This is the line which you will come across if by any chance, if by any chance you, if by any chance you read the NCRT, which I have told you that you have to read, but I'm sure you haven't read that till now. Okay, yeah, so if you by chance read the NCRT, you'll come across this line that positively charged ions present in the sea of electrons are known as kernels. These are kernels, and this is how metallic bonding takes place. This is how metallic bonding takes place. Okay, I hope you're clear with the concept that what is metallic bonding and what are the kernels. How do we define kernels? Yes, perfect. Now let's move a little further. First, if you want to write it, you can write it down, and then we'll move further. Okay, write it down, my dear students. Okay, I hope you've written it. Now let's move forward. Now let's move forward, my dear students. Now, the first point says that the melting point is fairly high, but it is comparatively less than the ionic solids. I told you that ionic bonding is the most strongest bonding. Ionic bonding is strongest. If yes, covalent bonding is the strongest. Then you have ionic, and then you have metallic bonding, my dear students. So the bonding here, I can write that ionic bonding is a little bit stronger than the metallic bonding. And that is the reason the melting point is high. Yes, metallic bonding. In your metallic bonding, yes, the melting point is high, but it is comparatively lesser than the ionic bonding, because ionic bonds are even stronger than the metallic bonds. Okay, yes, perfect. So I hope you're clear with this point. Second, unlike the ionic solids, they are malleable and ductile. Now let's try to understand what is malleable and what is ductile. Okay, what is malleable? Write it down. Tendency to get converted into sheets. The tendency to get converted into sheets is known as malleability, right? Yes. So malleability is the tendency to get converted into sheets. And what is ductility? What is ductile nature? Tendency to get converted into wires. Tendency to get converted into wires is actually known as the ductile nature. Okay, so what does it say? It says that your metals have the tendency to get converted into sheets, as well as they can be converted into wires. Okay, so now let me explain you why does this happen. Okay, if you see, my dear students, you have Zn2 plus present in the sea of electrons. Electrons don't have a definite position to be present. Okay, so what happens is, you have your metal ions. If you try to convert them into sheets, you apply pressure from both the sides. What will happen? Since the position of your electrons is not fixed, they can move around. Yeah, they'll move around, my dear students, and they can be converted into sheets. There will be nothing known as repulsion, because the position is not fixed, right? Yes, so they'll move a little here and there, and you will get the sheets, right? Yes, so they can be converted into sheets. Similarly, they can also be converted into wires, right? Because the position is not fixed. Okay, so we can say that unlike the ionic solids, they are malleable and ductile. Ionic solids were not malleable and ductile, but your metallic solids are malleable as well as ductile. Okay, I hope it is clear. Perfect, my dear students. This point is important. All these points are important. Questions are asked from these particular points. Next, when potential difference is applied, the mobile electrons can move, making the metallic solid a good conductor. Now see, I told you for a metal or a element to be a good conductor of electricity, it should have good charge carriers. And what are charge carriers? Either they could be free electrons, or they could be free ions, right? Yes. Now it is saying that your metallic solids are good conductors. Why are they good conductors? Because you can see that you have free electrons present. They don't have a fixed position. They are free. Yes, ma'am. Since they have free electrons present, they can carry the charge and they are good conductors of electricity. Okay, yes. So this is the basic thing here. When potential difference is applied, the mobile electrons can move, making the metallic solid a good conductor. Okay, so it is a good conductor. This is very important, my dear students. Please write it down and then we'll move forward. Okay. Okay. I hope you've written it. I hope you've written it. Pause the video and then you had to write. I'm not going to give you time because it will take a lot of time again. Okay. So now, my dear students, that was all about metallic solids. That was all about metallic solids. Now we will be discussing about the molecular solids. Okay. Now, ionic solids had very strong interactions, ionic interactions. Then we talked about metallic solids. Metallic solids also had a good interaction. Okay. So now we will be talking about molecular solids. Okay, what are molecular solids? Molecular solids, what will be their constituent particles, my dear students? Since I'm talking about molecular solids, then definitely their constituent particles would be molecules. Yeah, perfect. Now let's talk about the force of interaction. What will be the force of interaction? In molecular solids, you generally have van der Waals forces of interactions. You have van der Waals forces of interaction. I'll make you explain, don't worry, but you have studied all these in the chemical bonding chapter. So here, the force of attraction would be van der Waals interaction. Okay. Hydrogen bonding, dipole-dipole interaction, and van der Waals of London forces. London forces. Right? I'll make you explain. Don't worry. I'll make you explain. I know. Though you were supposed to know all of the interactions because you have studied in chemical bonding, but I know all of you. So I'll also make you explain each and every interaction one by one. Okay. For the time being, you can write it and then we'll move forward. Okay. I hope you've written it. Now, my dear students, now let's talk about each and every three. I told you molecular solids could exist in three major types. It could be non-polar molecular solids, polar molecular solids, and hydrogen bonding molecular solids. Now we'll discuss each and every one in detail. Okay, so the first is non-polar molecular solids. To understand this, we actually need examples. So let's take a few examples. Okay, so if I talk about non-polar molecular solid, then the examples would be, you need non-polar molecular solids. So you will have CO2, you will have SO3, etc. Yeah, these types of solids. Now I'll explain you why are they non-polar. Okay, if you talk about CO2, you have carbon here, you have double bond over here, double bond over here. I hope all of you remember how to calculate the dipole moment. Since oxygen is more electronegative, so the dipole moment would be this direction. Since oxygen is more electronegative, this will cancel out and your net dipole moment will come out to be 0. Net dipole moment will come out to be 0, right? Yes. Similarly, your SO3 is also symmetrical molecule and that is the reason it is non-polar in nature. So the elements which are symmetrical in shape, they will be non-polar molecular solids. Okay. Now let's talk about the dipole moment. Since they are non-polar, ma'am, what will be the dipole moment? 0. So can I say that the dipole moment here would be equal to 0? Yeah, perfect. Let's move forward. Next is force of attraction. Now, what will be the force of attractions? Now, my dear students, since they are non-polar in nature, they will have the weakest forces of interaction. And the weakest forces of interaction that exist in non-polar molecules are London forces. It is a type of van der Waals force, my dear students. It is the weakest force which is present in the non-polar molecules. Okay. So, the force of interaction would be London forces. This is the weakest force of interaction. Okay. Yes, perfect. Now let's talk about melting point. Since there is a very weak force of interaction between the molecules, I can say that it is the weakest, so the melting point will also not be very high. You don't need a very high temperature for breaking the very strong, very weak interactions, right? Yes. So it will have a fairly low melting point. So can I say that it has a low melting point? Yes, so it has low melting point. Okay, let's talk about the last part, which is hardness. Now, my dear students, if you talk about the solid, you can see that the interactions are very weak. Weak London forces are present, so it cannot be a hard solid, it will be a soft solid. Okay, so we'll say that it is a soft solid. So it is a soft solid. Okay, this is what we need to know about non-polar molecular solids. Okay, please write it down and then we'll move forward. I hope you've written it. Now let's move forward. Now let's talk about the polar molecular solid. Now we'll talk about the polar molecular solid. So now, my dear students, when we talk about polar molecular solids, first pause the video, try yourself, and then I'll definitely explain you. Why am I here? I have to explain you, right? Yes. First try yourself. If I talk about polar molecular solids, then I know that the molecules will be polar in nature. The molecules will be polar in nature. Example, my dear students, HCl, SO2, etc. All these are polar in nature. I'll just make you explain how they are polar in nature. You have hydrogen and you have chlorine. Which of the following is more electronegative in nature? Obviously, chlorine is more electronegative, so you will have something like this. Okay. Yes, so you can see that there is a dipole moment shown here, so it is a polar molecule. Okay, since there is a dipole moment present here, so what will be the dipole moment? It cannot be equal to 0, so we can say that the dipole moment is not equal to 0, and that is the reason we are saying it to be a polar molecule. Okay, the next question is asked is, okay, fine, it is a non-polar molecule, it is a polar molecule. Now tell us, what is the forces of interaction? Now, my dear students, since you see that you have HCl, that is a dipole is involved. So here the interactions are dipole-dipole interactions. Here the interactions are dipole-dipole interactions, which are stronger than the London forces, which are stronger than the London forces. So can I say that the interaction here is dipole-dipole interaction? So the interaction here is dipole-dipole interaction. Okay, perfect. Now let's talk about the melting point. So my dear students, if you talk about the melting point, then what can we say? Melting point, obviously ma'am, it will have a high melting point as compared to the non-polar molecules, because the interaction dipole-dipole is stronger than the London forces. I told you, I had given you that order of the interactions that you need to remember. Now, but still it will have very low melting point. These forces are also not very strong forces of interaction, so we'll say that it has fairly high melting point. No, let's say it still will have low melting point, but more than non-polar molecular solids. Okay, perfect. I hope you're clear with this. Now let's talk about the hardness. Still, my dear students, since the interactions are not very strong, so these are also considered as soft solids. So we'll say these are soft solids. Okay, so these are soft solids. Okay, perfect. I hope you're clear with this. Please write it down and then we'll move forward. Can I have water till then? I'll have water and then we'll move forward. Okay. Okay, let's move forward. Next type of solid, which is hydrogen bonded molecular solid. Okay, Now, what is hydrogen bonding? That is something which you need to understand. See, my dear students, hydrogen bonding is only and only possible if your hydrogen is connected with some electronegative element out of nitrogen, oxygen and fluorine. Okay, nitrogen, oxygen and fluorine. Hydrogen bonded with these three electronegative elements forms hydrogen bonding. Let's take an example. Let us say that I had H2O. Okay, so you had oxygen here, you had hydrogen here, you had hydrogen here. Now, you know that hydrogen is bonded to a very electronegative element, which is your oxygen. Okay, so it will have partial negative charge, it will have partial positive charge. Again, you have oxygen here, you have hydrogen here, you have hydrogen here. You will obviously have a lot of water molecules. Okay, so I can say that here partial negative charge, partial positive charge. Now see, hydrogen bonding is always between a hydrogen bonded to a electronegative element. Okay, so this is partial positive, this is partial negative, so they will have some interaction, and this is known as your hydrogen bonding. So hydrogen bonding is only possible when your hydrogen is bonded to these three electronegative elements. Okay, and this is how hydrogen bonding takes place. And hydrogen bonding is a little stronger than the dipole-dipole interactions. Okay, this also I told you in the order I gave. Okay, so let's take example. Example is H2O, NH3, etc. Okay, yeah, let's talk about the forces of interaction. You know that the force of interaction would be hydrogen bonding. Okay, so can I say that it would be hydrogen bonding? Now let's talk about the melting point. Since this interaction is even stronger than the ion dipole, even stronger than the dipole-dipole interaction, hydrogen bonding is a stronger bonding. Okay, so we'll say that melting point would be fairly high, because the interaction of hydrogen bonding is a little stronger. Okay, yes. Now what will you comment on the hardness? It will be a hard solid. It will be a hard solid. Okay, since the interaction is strong. I hope you're clear with this. You can pause the video, write it down, and then we'll move forward. I hope you're clear with this. Let's move forward, my dear students. Now you have covalent solid. Now let's talk about the covalent solid. Okay, covalent solids are also known as network solids. There is another name given to them, which is network solids. Is it written here? No. Then you can write it also known as network solids. Now let me tell you, this is the hardest solid that we can say. This is the hardest solid, or we can say that the covalent solids have the highest melting point. This interaction is the strongest. Now why is this the strongest? Till now, when we talked about interactions, we only talked about the interactions in space. Let's say you had an ion, let's say you had another ion, and they had some interaction. But were they sharing something? No, they were not sharing something. It was only in the space everything was happening, right? Yeah. But what actually happens in covalent bonding is there is a sharing of electrons. You have one atom which shares its electron, then you have another atom which shares its electrons, and you get a bond AB where both of them are sharing their electrons. Since there is a sharing of electrons, and that is the reason this is the strongest interaction, because till now the interactions were just in space, but here, my dear students, there is some quantity, some sharing happening here, and that is the reason it is the strongest bonding. Okay, now let's take example, and let me tell you, you only need to remember these examples. You don't need anything else other than that. The examples are silicon. You have silicon carbide, you have SiO2, you have ALN, you have diamond, you have graphite, These are the few examples that you need to remember, for covalent solids. Okay, yes, I hope you're clear with this. First, did I give you time to write it down? Yeah, I gave you. If try to the covalent bonds are extended throughout the solid structure. I'll make you explain that as well. Don't worry, I am here. I'll make you understand. Till then, try to understand this, my dear students. I hope you've written it. Now, my dear students, now let's understand this particular part, that the covalent bonds are extended throughout the solid structure. How are they spreaded throughout the solid structure? Let's take the example of diamond. Diamond is made of carbon, where carbon is tetrahedrally bonded to the other carbons. Okay, so what does this mean? Let's talk about diamond. Can I write here diamond? Yeah. So you have carbon present here. It is tetrahedrally bonded to 4 other carbons. Okay. Now each carbon in this will be tetrahedrally bonded to other, right? Yes. So here you will have carbon, you will have carbon here, you will have carbon here, carbon, 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 and you will have carbon here, carbon here, carbon here, and this also goes on. Okay. So this also goes on. I hope you're clear with this. Now, what do I want to show you here, that, my dear students, it is a network which keeps on growing, and keeps on growing. And that is the reason we call it as a network solid. It forms a network, kind of a network. And since here every bond is formed by the sharing of electrons, it is a very strong bond. And you know, diamond is the hardest solid we know in the world. Diamond is the hardest solid we know in the world. It has a melting point around 4000 degrees Celsius. This is so high. This bonding is so strong. You can just have a look here. Right? Yes. Perfect, my dear students. So you can draw this diagram if you want to, and then we'll move forward. I hope you've drawn it. Now let's move forward. Let's talk about the melting point. We'll say that it has very, very high melting point. So can I say that it has very high melting point? Okay. Next is hardness, my dear students. It is the hardest. We know that diamond is the hardest solid we know. So we can say that very hard solids. Okay. These are very hard solids. Let's talk about the electrical conductivity. These are poor conductors of electricity because all the electrons are bonded and there are no free electrons present. So poor conductors. Okay. Or you could say non-conductors. Perfect. Yes. Pause the video, write it down. Now, after all learning everything about the covalent solids, graphite came into the picture. And graphite said, wait a minute, if you are trying to understand each and everything, I'll make an exception for you. I'll behave exceptionally. Whatever you think, I'll behave in a very different way. And that is what graphite did. Do you know that graphite is a soft solid? It is a soft solid. Yeah, it is graphite. I hope you can see here. Now, my dear students, graphite is a soft solid. First thing, since all the covalent solids are hard solids, but your graphite is here and it's saying that it is a soft solid. The other thing that graphite says that I am a soft solid and I am a good conductor of electricity. I am a good conductor. Also, it is a good conductor. So, it is behaving differently in two manners. They were hard solids covalent, but graphite is a covalent solid, yet it is a soft solid. Okay. It is generally used in lubricants. You might have played carom, right? You use a lubricant, you use a powder there so that carom, you can play carom more easily. Those what do we call them? I have no idea what do we call them, but they can slide very easily, right? Yeah, that is the reason we use the powder. The powder which we use is actually made up of graphite, and graphite here, my dear students, actually acts as a as a lubricant. Okay, so ma'am, we can say that it is soft in nature. Obviously it is soft in nature. Okay, the other thing is it is a good conductor of electricity. All the covalent solids are poor conductors or non-conductors, we would say, but graphite is a good conductor. Now we have to understand why is this happening. So now let's try to understand that, and that could be understood only and only by seeing the graphite structure. So here you have the graphite structure, and you'll have to understand the structure to have a little more clear picture. Okay, so my dear students, in graphite structure, what happens is there are layers. In its structure there are different layers formed. Okay, so let's say this is layer A and this is layer B. So two layers, my dear students, this layer and this layer are connected to each other by weak van der Waals forces. So these interactions between two layers are weak van der Waals interaction. These are weak van der Waals interactions. Okay. Now, I'll make you understand even a little bit more. Let's say this is your carbon. Let's first try to understand that. You have a layer A, you have a layer B, and you have weak interactions in between them. So you have these layers, and these two layers have weak interactions, so they can slide over one another easily because the interactions are not very strong. And that is the reason it behaves as a lubricant, and that is the reason we call it as soft solid. That is the reason we call it as soft solid. Okay, so can I say that it can be used as a lubricant? Perfect. Okay, now let's try to understand why is it a good conductor of electricity. Okay, for to conduct electricity you need free electrons, you need charge carriers. Okay, so now my dear students, what actually happens is you have carbon here, it is bonded to 3 other carbons. Okay, and you know that carbon has 4 valence electrons, so it has 1 electron free. Every carbon has 1 electron free. Right? Yes. So can I say that though it is covalently bonded, but there are free electrons present, and since there are free electrons present, so they will conduct electricity. Yes, that is the reason graphite acts as a good conductor, because it has free electrons present in it. So graphite behaves a little bit different from the properties we have studied about covalent solids, so we need to know about those. Okay, please write it down and then we'll move forward. Can I have water again? You write it down, I'll have water, and then we'll move forward. Yes. I hope you've written it. Now let's move forward. Now, my dear students, here are a few questions to test what I told you. You actually understood, or you were just like, okay ma'am, fine, we are reading it. No, you have to understand, and that is the reason you have to solve the question. So try to solve the questions. The first question says that classify the following solids in different categories based on the nature of the intermolecular forces. Okay, you have sodium sulfate, so you have Na2SO4. Then you have copper, then you have benzene, then you have urea. Urea formula is NH2C double bond O NH2. Okay, I'll write urea here. Then you have ammonia. Then you have water. Then you have zinc. Then you have, okay, you have zinc sulfide. Then you have diamond. Then you have rubidium. Then you have argon, silicon carbide. Okay, now let's try to understand each and every one individually. Okay, so now if you have Na2SO4, my dear students, can I say that you have Na plus and you have SO4 2 minus? Yes, since it is two oppositely charged ions, so can I say that it is an ionic solid? Is there any problem with that? No, it's absolutely right. Perfect. This is how you'll classify it. Now let's talk about copper, my dear students. What is copper? Copper is a metal, metallic solid. It will be a metallic solid. Okay. Next is benzene, my dear students. Benzene is a molecular solid, and that too non-polar molecular solid. Okay. So I'll say that it is a non-polar molecular solid. Okay. Next is urea. Now, my dear students, if you see here, urea has a dipole present here. So, it is a molecular solid, but it is a polar molecular solid. Okay, so it is a polar molecular solid. Okay. Let's talk about NH3. Now, NH3, nitrogen is bonded to hydrogen. That is, hydrogen is bonded to an electronegative element, nitrogen. So, here you will have hydrogen bonding. So, can I say hydrogen bonded molecular solid? It is a hydrogen bonded molecular solid. Let's talk about the other, water. Again, hydrogen is bonded to electronegative oxygen. So, hydrogen bonded molecular solid. Yeah. Let's talk about the others. You have zinc sulfide. You have Zn2 plus and you have SOS2 negative. So it is a ionic solid. Okay. So this is ionic solid. Let's talk about diamond. What is diamond, my dear students? Ma'am, diamond is a covalent solid. Yes. So it is a covalent solid. Let's talk about rubidium, my dear students. What is rubidium? Rubidium is a metal. So it will be a metallic solid. So it is a metallic solid. Now, what is argon? Argon is a non-polar molecular solid. It is non-polar in nature. It is a molecular solid. So, it will be a non-polar molecular solid. What is silicon carbide? We just learned a few examples of covalent solids and it was one of them. So, it is covalent solid. Right? Yes. So, this is how you will classify all the different types of solids. I hope you're clear with this. Please pause the video, write it, and then we'll move forward. I hope you've written it. Let's move forward. Let's try another question. The question says that solid A is very hard. Solid A is very hard. It is electrical insulator in solid as well as in molten state. You have a solid A which is a insulator. It is not a conductor of electricity neither in solid state or liquid state. So this is a covalent solid, right? Yes, we can find out from this thing that we can say it is a covalent solid. Right? Yes. And melts at extremely high temperature. What type of solid it is? It is a covalent solid. If it was a bad conductor in solid state and good conductor in liquid state, it would have been your ionic solid. Okay, perfect. You can pause the video, write it down, and let's move forward. Why are ionic solids conducting in the molten state and not in the solid state? Because in the molten state, my dear students, you have free ions present, and since you have free ions present, they can conduct electricity very easily because free ions are charge carriers. Okay, so if you want to write it in your language, please write it down. I have given you the answer. Perfect. I hope you're clear with this. You can write the answer. Next question. Next question says that what type of solids are electrical conductors, malleable and ductile? They are electrical conductors, they are malleable and they are ductile. Which were these? These were your metallic solids. So your answer would be metallic solids. Right? Yes. Perfect, my dear students. I hope you're clear with this. Easy, right? Yes. Let's move forward. Classify each of the following solids as ionic, metallic, molecular. It is molecular, network, covalent, or amorphous solid. Okay, so let's try to answer each and every part. Okay, the first is tetraphosphorus decoxide. So you have P4O10. It is a symmetrical molecule. So can I say that it is a molecular solid? It is a molecular solid. Let me write it as molecular solid. Okay. Let's move forward. Next is ammonium phosphate. My dear students, you have ammonia and phosphate, two different ions. So it is a ionic solid. So it is a ionic solid. Silicon carbide. It is a covalent solid. I2. What is I2? Non-polar molecular solid. So it is a molecular solid. Right? Yes. Perfect. Let's move forward. P4, my dear students. What is P4? Non-polar molecular solid, right? Yes. So it is a molecular solid. Graphite is a covalent solid. Brass is a My dear students, brass is actually a alloy. So let's leave it right for now. When you'll study metallurgy, you'll try to answer it a little bit more. Don't do this right now. Okay. Let's talk about rubidium. Rubidium is a metallic solid. It is a metallic solid. Okay. LiBr is a ionic solid. And if I talk about silicon, silicon was a covalent solid. Right? Yes. So easy. If you have studied each and every part very thoroughly, you'll be able to answer each and every part of it. Okay. Yes. Perfect. I hope you're clear with this. Please pause the video and write all the answers. Perfect? Yes. Okay, my dear students. Till now, everything is crystal clear, right? Now let's move forward to the next topic, which is lattice. Now we are going to actually start the crystalline solids in detail. What actually is a lattice? Okay, let's try to understand a lattice. Okay, now my dear students, whenever we construct a building, what do? We use a brick, we add one brick, then we add another brick, 3 bricks, and then brick on brick on brick, and we get the building, right? Yeah. So this whole repeating of your brick is actually called the lattice. This whole repeating of your bricks and forming a wall is actually a lattice. Okay, that in total is known as a lattice. And if I talk about that one brick, what is that known as? That is your unit cell. You will get all the definitions, don't worry. For the time being, you have to understand. What is unit cell? The brick is the unit cell. Since we are repeating the brick and forming a wall, what will be that? That will be a lattice. So lattice is a collection of units of cells, right? Unit cells. Or a repeating unit cell gives you a lattice. Okay. Now lattices can be of different types. It could be 1D lattice. That is one-dimensional lattice. So this means that you will have a lattice in one particular axis. So your lattice could be something like this. In any axis, x-axis, y-axis, z-axis, it doesn't matter, but it is in one particular axis, so it will be a one-dimensional lattice. Let's talk about the two-dimensional lattice. Two-dimensional lattice. So if we talk about a two-dimensional lattice, my dear students, what will it be? Ma'am, since you're talking about two dimensions, so it will be in two different axes. Let's say x and y axis, so your lattice would be something like this. Are we playing a game or what? I hope all of you remember. I hope you might have played this game, because I have played this game a lot. Something like this. So can you see one thing here, my dear students, in this two-dimensional lattice, that this particular square is repeating again and again. So this one particular cell will be known as your unit cell, and since it is repeating again and again in two dimensions, so it will be your two-dimensional lattice. Okay, let's talk about the three-dimensional lattice now. For three-dimensional lattice, we will need something like this. Okay. I'll just make you understand. Don't worry. When ma'am is here, why to fear? Right? See, connect these four and repeat it. Repeat it. Repeat it. Repeat it. Repeat it. And repeat it. See? Then repeat these. Right? Now connect these. See, I hope you're getting the point. Okay, perfect. Now, if you see, this one cube is repeating itself all over again and again. Since it is repeating itself all over again and again, so I can say that this is my unit cell in the three dimensions. So a square or a cube or any Any cube or cubic or rhombohedral or anything, any unit that is repeating itself in the three-dimensional lattice will be known as the unit cell of the three-dimensional lattice. Okay, and this whole axis, this whole lattice in total will be known as the three-dimensional lattice. Okay, so this is the basic idea of the unit cell and the lattices. I hope you're clear with this. Please pause the video, you can draw it, and then you will see the definitions in the next slide. Okay, perfect. Let's move forward. What is space lattice? It is an imaginary collection of the infinite number of points with a regular and repeating geometry. The geometry should be regular and repeating. Okay, yes, perfect. What is unit cell? The smallest repeating unit of the space lattice, the smallest unit which will get repeated again and again, and you get your lattice, will be known as your unit cell. Now, my dear students, to define a unit cell, we need some cell parameters. How can we say a unit cell is a cube? How can I say a unit cell is a cuboid? How can I say a unit cell is a rhombohedral? It depends on the cell parameters. And now, my dear students, it would be very difficult for me if I want to study the whole wall. But what if I study only the smallest part which is repeating again and again, that is your brick, and then I'll get the idea of the complete wall? Yes, so this is what we do in the solid state chapter. We find out the smallest unit, we study that particular unit cell, and then we get the idea about the whole lattice. Okay, so now to understand this, we need to have a very clear understanding of the unit cell, and for unit cell we need the cell parameters. So now we'll be discussing about the cell parameters. Cell parameters define the geometry of the unit cell, whether it is a cube, whether it is a rhombohedral, or what, right? Yes. The imaginary points are known as lattice points. Now, my dear students, imagine I gave you this unit cell. In this unit cell, the points on this lattice, this point, this point, this point, this point, all these points are the lattice points. All these points are the lattice points. So, all the points on the lattice are known as the lattice points. Okay, perfect. I hope you're clear with this. Pause the video, write it down, and then we'll move forward. Okay, I hope you've written it. Now let's try to understand the cell parameters. Okay, for understanding the cell parameters, I need to draw a unit cell. So let me draw a unit cell. Okay, let's say this is your unit cell. Now, if we talk about this unit cell, my dear students, let's talk about the axes. Okay, you have x-axis, you have y-axis, and you have z-axis here. Okay, these are the axes. So can I take this particular point and let me tell you the edge length along A is known as, x-axis is known as A. So this will be the A edge length. So A is the edge length, okay, along the x-axis. What is y? Edge length along y is known as B. Edge length along y is known as B. So this is something known as B. And the edge length along z is known as C. So the edge length along z axis is known as C. So can I say that A is the edge length along x-axis, B is the edge length along y-axis, and C is the edge length along z-axis. Okay, so the three parameters are the edge lengths A, B, and C. After that, my dear students, I'll just let you know a trick. With that, you can also find the angles between the edges. Okay, so you write A, you write B, you write C, you write alpha, you write beta, you write gamma. So now, my dear students, how can you find out which angle is which? Let's say I want to see the alpha angle. So just put a hand over it, right? Yes, you will see that the two edges which are still visible, the alpha will be the angle between these two. So alpha is the angle between B and C. So you have B, you have C, so this angle is known as alpha. This angle is your alpha angle. Okay, now let's try to understand this. Which angle is beta? Between A and C. So between A and C is your angle beta. Now let's see this. Between A and B the angle is gamma. So between A and B the angle is gamma. Okay, so this is how you find the angles. Okay, so can I say that alpha is the angle between B and C? Angle between B and C. Beta is the angle between A and C. And gamma is the angle between A and B. Right? Yes. So my dear students, A, B, C are the edge lengths. Alpha, beta, gamma are the angles between them. Okay. These 6 parameters together give us the complete information about a unit cell. These 6 parameters together give us the complete information about the unit cell. So A, B, C represent the edge length of the unit cell along the 3 axes. The plane may be, it is not written here, but I'll tell you that the angles actually give the angles between the edges, and these in total give you the complete information. So these 6 together are known as the cell parameters. Okay, so you can pause the video, you can write it, and then we'll move forward. Okay, perfect. So the 6 parameters are A, B, C, alpha, beta, and gamma. For you to understand and have complete knowledge of a unit cell, you need to know all the 6 parameters. Okay. Geometry of the unit cell defines the crystal system. Which unit cell it is? It is a cube, it is a cuboid, it is a rhombohedral, it is a tetrahedral, it is a triclinic. Which unit cell it is given by the geometry of that crystal system. There are a total of 7 crystal systems. Now, depending on the values of these 6 parameters, there are total, my dear students, 7 crystal systems possible. Now we'll be understanding which 7 crystal systems are these. Okay, so for that you need to write it down and then we'll move forward. I hope you've written it. Now let's talk about the 7 crystal systems, and you need to know about each and every unit crystal system, my dear students. It is very important. Questions are asked from these, so you need to remember these. The first is cubic, the second is tetragonal, third is orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. You have been given their informations as well. If this table is not visible, don't worry, just open your NCERT. You'll get exactly the same table and you need to remember this table. Okay, you can remember it as CTO, that is Chief Technical Officer, cubic, tetragonal, and orthorhombic. Then you will have rhombohedral everyone knows. If you know about rhombus, you can find the information about rhombohedral. Then you have hexagonal, monoclinic, and the triclinic. Okay, so these are a few crystal systems which you need to have complete information. Their angles, their edge lengths, everything is very important, my dear students. So you need to remember each and every thing. Okay, so if you want, you can pause the video and draw these, but if you can't, then write from the NCERT, you can understand this particular part. I hope you've written it. Now let's move forward. Okay. Now, my dear students, I hope all of you can understand that there are 4 different types of arrangement. Now see, I told you that there are 7 different types of crystal systems. It could be any type depending on the cell parameters. Okay. Now, my dear students, how you will arrange atoms into them, that is also a very major role to play, right? Yes, let's take an example of cube. I'll make you explain the all the arrangements with the cubic system only, and then you can incorporate them in the other crystal systems as well. One by one we'll be discussing about that. Okay, so there can be 4 types of arrangements for a given geometry of the unit cell for a given crystal system. You have 7 different crystal systems, and you can have different types of arrangements in that. That is, let's say you have a house and you have people coming over to your house. Okay, you have guests coming over. Obviously you'll have to decide that which guest will stay in which room. That is what you will be doing the arrangement, right? Yes. So same way, my dear students, atoms are guests and they come and stay in the crystal system. So crystal system can arrange those atoms in different ways, and those arrangements are majorly of 4 types. Now you have 7 different types of houses and you have 4 different types of arrangements. So this is how you can arrange the people. So now let's take one unit crystal system. Let's take cubic crystal system and understand the arrangements. Okay, so I'll be taking cubic crystal system. We will only discuss cubic crystal system. Okay, now let's take examples of each and every crystal system. Let's say the first arrangement. Your first arrangement is your primitive arrangement. Primitive arrangement is the most basic type of arrangement, and in this arrangement, my dear students, nobody took a lot of effort. They just said that atoms will come and they'll sit on the corners of the crystal system. You have a cubic crystal system, and in primitive, only and only corners could be atoms can only take the places of the corners. Okay, so can I say that one atom will sit here, the other atom can sit here, the other atom can sit here, the other atom can sit here, 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 no, not here, it is not a corner, here it is a corner, here it is a corner, and it is also a corner. So basically, my dear students, 8 corners can be occupied by the atoms, and this is the primitive arrangement. So in primitive arrangement, all the corner atoms are occupied, and that is known as the primitive arrangement. Okay, and in cubic crystal system, we call it as primitive cubic crystal system. Okay, or you can say that primitive cubic system. So now here, my dear students, whenever you name something like this actually, the first word actually gives you the arrangement, type of arrangement. It is primitive. Okay, so type of arrangement is primitive. And your cubic system gives you the type of system, type of crystal system. Okay, perfect. So this is the primitive cubic system. Okay, now let's move forward. The next type is, you can see, when the constituent particles are present at the corners only, it is known as the primitive arrangement. Okay, let's talk about the other arrangement. The other arrangement is body centered arrangement. So in body centered arrangement, my dear students, the primitive is fixed. That can happen, but now you can place an atom at the body center as well. Okay, so the difference is that atoms will be present at corners. Atoms will be present at corners, but they have one more place to sit, and that place is, my dear students, center of the body. So this is the center of the body, and in a body centered arrangement, atom can sit in the center as well, and corners will definitely be occupied. So this type of system is known as body centered cubic system. Okay, so here, my dear students, body centered gives you the arrangement, type of arrangement, and your cubic gives you the crystal system. which crystal system you are using. You can write here your rhombohedral as well. Then in rhombohedral, all the corners will be occupied and the center of that rhombohedral will be occupied, and you will say body centered rhombohedral. So this is how you can use the different type of arrangements in the different crystal systems. So when the constituents particles are present at the corners as well as the center of the unit cell, it is called the body centered arrangement. Okay, I hope you're clear with this. Pause the video, you can write it, and then we'll move forward. Let's move forward. Next, face-centered arrangement. In face-centered arrangement, my dear students, your atoms are still present at the corners. They can be present at corners. Okay. Other than corners, they can be present at the center of all the faces. You have 6 faces. They can be present on the center of each face. That means that just consider the walls center. You have 6 walls in a cube and all the center parts can be occupied. So this is the face centered arrangement. So you call it as face centered cubic crystal system. Okay, so this is your arrangement. This is your arrangement, and this is your crystal system. Okay, perfect. I hope you're clear with this. This is how you will be writing the face-centered cubic crystal system. Okay. So it is written, when the constituent particles are present at the corners as well as the center of the faces, it is called the face-centered arrangement. Okay, let's discuss about the last type of arrangement, and that last type of arrangement is end-centered arrangement. What happens in an end-centered arrangement is you have atoms present at the corners. And you have atoms present at any one opposite faces, any one pair of opposite faces. This means that let's take these opposite faces, then only on these opposite faces the atoms could be present, or just erase this, and these opposite facing faces centers, your atoms could be present. Any one pair of opposite facing faces center atom can be arranged. Okay, just make a sentence out of it. Okay, I hope you're clear with this. Now you can draw this, and this would be known as end centered cubic crystal system. Okay, so this will be your arrangement, and this will be your crystal system. Okay, I hope you are clear with this. These are the 4 different types of arrangements that are possible, and you have 7 different crystal systems. It is written here as well. When the constituent particles are present at the corners as well as the center of any 2 opposite faces, it is called the end-centered arrangement. Okay, first write it down and then we'll move forward. I hope you've written it. Now, my dear students, just see. Now you know that there are 4 types of arrangements, and these 4 types of arrangements can be present in any one of the crystal system, right? Yes, you have 7 crystal systems and you have 4 different types of arrangements. So can I say that 7 into 4, total 28 unit cells, 28 different unit cells can be present? Yes, ma'am, you can say that. And that is what is actually calculated theoretically, that these 4 arrangements can be present in each of the crystal systems. So total 28 different unit cells can be present in this whole world, right? And these are known as Bravais lattices, and these are known as Bravais lattices. The name is given as Bravais lattices. Since 4 arrangements are possible with each crystal system, so 7 into 4, that is 28 unit cells are possible theoretically. These unit cells are not equally distributed among the crystal system. Let me tell you, these are known as Bravais lattices. These are known as Bravais lattices. Now, since 28 unit cells are too much to handle, what actually happens is our world actually loves symmetry. So all the 28 crystal systems are not available in the world. They are not possible. They are not present, or we could not find them. We could only say that only out of these 28, 14 of the unit crystal systems are present because of the symmetry, because these 14 have symmetry, the others do not have symmetry, and our universe loves symmetry. Okay, so only 14 out of these 28 unit crystal systems exist in nature. System symmetry is in consideration. These unit cells are not equally distributed. We'll see which of the following are possible, and you have to learn that as well. Okay, yes, pause the video, write it, and then we'll move forward. These are the crystal systems that are possible. For example, let's say cubic crystal system. In cubic crystal system, my dear students, only 3 type of arrangements are possible. The end centered arrangement is not seen. Okay, if you talk about the tetragonal, only 2 type of arrangements are possible. The others are, due to symmetry, they are not possible. In orthorhombic, it is one and the only which has all 4 types of arrangements, and that is the reason it becomes an important part, because the question is generally asked that which of the following is possible, which of the following has all the 4 types of arrangement. It's only one, and that is your orthorhombic. Okay, so you need to remember that which of the following arrangement is possible in which crystal system. Just remember that all the primitive is available in all. Orthorhombic has all the 4. So you might have learnt these are 7, 8, 9, 10. 10 you have learnt. Okay. Cubic crystal system, you'll study so much in this particular chapter that you'll remember that only these 2 more are available. So you just need to remember this and this. Rest all you know. Rest all you have learnt just right now. Okay, so just remember this. Generally question is asked, and most of the times orthorhombic question is asked, that which is the crystal system where all the 4 types of arrangements are possible. It's orthorhombic. I hope you're clear with this. Perfect, my dear students. You can pause the video, draw the diagrams, and then we'll move forward. Okay, so here are the diagrams of the unit cells if you want. Okay, these are the beautiful diagrams of the crystal systems. If you want, you can just go through them. They are just for your knowledge. Generally it is not you are not asked to draw the diagrams, but yes, you need to know the alpha beta alpha ABC and alpha beta gamma values that I told you. Okay, now let's try to solve a few questions and have a grip on what we have studied today. Okay, the first question says that the most unsymmetrical and the most symmetrical system are respectively. You have to tell which is the most unsymmetrical and which of the following is the most symmetric of the following. My dear students, the most symmetric is cubic crystal system, because it has A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. Okay, and your triclinic is one which is the most unsymmetric, because in triclinic your A is not equal to B is not equal to C and alpha is not equal to beta is not equal to gamma. Okay, this is something very important for you. This is your triclinic, the most unsymmetric, and this is your cubic, the most symmetric. Okay, remember these 2. Generally question is asked from these 2. Okay, perfect. Let's move forward. Next is that in primitive cubic unit system, the atoms are present at, it is primitive, it is old, it only says that go and sit on the corners. So only corner atoms. Okay, yes, corners of the unit cell. So option A will be your correct answer. Perfect. Yes, let's move forward to the next. Next is, in the body centered unit cell, the lattice points are present at the primitive, that is corner part as well, and the center of the atom body crystal system. So corner and the center of unit cell. So option B will be your correct answer. Okay, perfect. Let's move forward to the next question. Last question for today's session. In the face centered unit cell, the lattice present are corners and all the faces centers, right? Yes, so corner and the face centers of the unit cell. So option C will be your correct answer. Perfect. With this, let's end our session today. We have studied a lot of things today. Today's topic was a little theoretical, so you need to go through all the part. You need to read the NCERT. I am focusing again and again for this particular part only. After this, I'll not ask you to read the NCERT, but for the theoretical part, please go through the NCERT. You need to remember all the crystal systems, their cell parameters, and in which of the following arrangements are possible. These are a few questions which are mostly asked, and you have to answer them. Okay. Yes, I hope you enjoyed today's session. You learned a few things, and you'll definitely do what I have asked you to do. You will solve the DPP as well. We'll meet in the next lecture. All the very best. Thank you so much.